So what is the Cannizarro reaction and why is it useful to us? Well, the Cannizarro reaction is a reaction that's similar in idea to the aldol, with the exception that we're going to be utilizing some characteristic of our R group right here. Um, basically, our R group needs to be some group that does not, oops, some group that does not bear any sort of alpha hydrogen. So what does that mean? It means we're looking at aryl groups for our. You can also be looking at alkyl groups that are tertiary substituted. Those are also good options. Um, the results of performing the Cannizarro reaction is in best yielding of a 50-50 mix of your oxidized carbonyl and your alcohol. And that's the best yield that you can get from this. So going forward, what is this question mark above my reaction arrow? Well, in the very beginning of the video, I said it's similar in likeness to the aldol reaction, with the small caveat being that the R group is a little bit different. And so, if you remember from the aldol reactions, we used we used um, some sort of a base to pull off alpha hydrogens. And in this case, we don't have alpha hydrogens. And so what are we going to do? Well, if hydroxide doesn't act like a base, the only other thing it can do with a carbonyl is to act as a nucleophile. So let's go ahead and jump into the mechanism and talk about how that happens. And I'm going to do this with benzaldehyde as my R group that does not bear that alpha hydrogen. Great. And then we said hydroxide. And for the sake of it, I'm going to say potassium hydroxide. And I'm just intentionally writing down the potassium counterion because in the end I'm going to use it. I'm going to use it up here, right there. But for right now, we said the hydroxide is going to act as a nucleophile, so we're going to see it attack that carbonyl. So let's do that. Push the electrons down to that partially positive carbon. When you do that, you have to move electrons up to that oxygen. So we get our first intermediate. Just like this. Now from here, we need something else to do. So recognizing what's in solution, we have our intermediate with a bunch more of our hydroxide. So we're going to use that hydroxide again, and the only thing it can do here now is to again, or actually in this case, it's acting as a base, not a nucleophile. And the only thing that's acidic here is that alcohol OH. And so I'm gonna redraw this a little bit nicer, just like that. And so the extra pair of electrons on our hydroxide comes and pulls off that H, and electrons get flopped down onto that leftover oxygen there. We get our next intermediate. Which just looks like this. We have two anions in the same molecule, which is kind of weird, but it's very possible. And now from this point, we do an intermolecular hydride shift. So that's kind of a weird thing to say all at once, but I will show you what I mean. So now we're going to grab another one of our starting molecules, because again, those are just floating around solutions. So I'm going to take our starting molecule, so our benzaldehyde, and draw that above my arrow. And we need something to do with these ions, because they're very high in energy and they want to do something. So we're going to give them something to do. And this is the weird part of the Cannizarro reactions where we see a hydride shift happening because a bond's being made between carbon and oxygen. So when this happens, and when this arrow happens that I've drawn, we're going to break this hydride bond and it'll break through the hydrogen and see another one of these benzaldehyde carbonyls. When it does, it will attack that carbonyl, breaking the double bond to oxygen, and we will get our new intermediates, which just look like this. And we have our second molecule. And for the sake of it, I will draw in that hydrogen, just so we can see where it went. And now from here, it's just a matter of adding acid. Um, adding acid so that our carboxylic acid could be protonated, because at the time being right now, we do have water floating around in solution, because up in the second step right here, when our hydroxide pulled off that H from that alcohol, it turned into water, and so we do have some water floating around, but that can only get us so far into protonating one of our molecules. And so in the end, we end up getting an alcohol. And if it was perfect, we get a 50% mixture of our alcohol. And we'll get a 50% mixture of our carboxylic acid derivative. And at this point, it is the carboxylic acid salt, and that's why I drew in that potassium in the beginning, because at this point it is just a counterion for our carboxylic acid. And so again, I said we'll just add some acid, and we could protonate our carboxylic acid or carboxylic acid salt, so that it turns into that carboxylic acid.